Hi, I'm Amit, and today I'll be talking about our paper sampling from convex sets with a cold start using multiscale decompositions. This is based on joint work with Hariharan, Narayanan, and Piyush Srivastava at TIFR, and you can find the paper at the archive ID below. So first, let me explain what the basic problem is. So the problem is that you're given a convex body K, which is a subset of Rn, and you want to produce a point that is distributed approximately uniformly randomly over this body K. And this turns out to have a whole wide array of uses like in optimization, integration, etc. So the first question should be, how is this convex body K given to you? And this is given via something called a well-guaranteed membership oracle. So the membership part of this means that if you query a point X, this oracle just tells you yes or no whether this point is in the body K or not. And the well-guaranteedness means that you're given some smaller ball of radius small r, which is contained in this body K, and you're given a larger ball of radius capital R, which contains the body K. And typically the ratio of these two radii, r over r, is called the aspect ratio or sandwiching ratio of the body K, or rather of the oracle. And one specific case is when the body itself is a polytope, which is specified by a bunch of explicitly known linear inequalities over Rn. And what we would like is that in polynomial time, we want to produce a sample that is close to the uniform distribution on the convex body. This closeness is measured in terms of the total variation distance to the uniform distribution. And the polynomial running time is first in the dimension n, the aspect ratio r over r, and the log of the error parameter epsilon. So typically this problem is done using Markov chain Monte Carlo methods, which means that you come up with some random walk W, you start from some distribution and you run this random walk for long enough and show that, after a certain amount of time, the distribution you have is pretty close to the uniform distribution on the body. So two popular examples of such random walks are first a random walk on a uniform grid, and a very well-studied random walk is the ball walk, which is related to the famous KLS conjecture in convex geometry. Another walk is the hit and run random walk. And what this random walk involves is that, say, if you're at a point X right now, then to choose the next point Y, first you pick a uniformly random direction from, say, the unit sphere. And then from the segment, which is the intersection of this directional line with the convex body, you uniformly randomly pick the next point Y, right? And the other coordinate hit and run random walk, which is what we are interested in, is very, very similar to the hit and run random walk, except that instead of picking the direction from the unit sphere, you just pick it from one among the n principal coordinate axes, right? So you just pick one of these n directions. So if you take this, for example, then you, again, similarly, you pick the next point Y uniformly randomly on this segment. So generally, ideally, we would like that, you can take any of these random walks, you just start it at some arbitrary point, you run it for polynomial amount of time, and you're pretty close to the uniform distribution. Unfortunately, this is not always possible. So the thing is, okay, you cannot hope for mixing from a point necessarily, but what can you hope for mixing from? So what is an appropriate starting state? And towards this, we define this notion of warmness, which means that if you start your Markov chain from some distribution, you look at the density of this distribution with respect to pi k, or uniform distribution over the body. And if this density is bounded from above by m, then we say that this initial distribution we are starting from is m warm. And so first, suppose we have, a mixing time bound that is polynomial in this warmness parameter m. Then we only get rapid mixing if m is polynomial in the dimension n. And this setting where m is polynomial in the dimension n is called a warm start, right? And ideally, we would like that we can get mixing time even we can get a polynomial mixing time even in the setting where m is, say, e to the poly of n, which is called a cold start. And it turns out that if you manage to show mixing from a cold start, you can typically do just a little bit more work and show that the random walk even mixes from a point, which is the ideal case, as long as this point is not extremely close to the boundary. So let us next get to how you actually show that these random walks mix rapidly, which is done using conductance, which is an analog of Cheeger's constant in random walks on graphs. So first you define the conductance of a set S. So in our setting, what this means is that to define the conductance of a set S, first you uniformly randomly draw a point from the set S, and then look at the probability that one step of the random walk escapes the set S. So in some sense, if this conductance is low for a given set S, it indicates that the random walk is likely to get stuck in the subset S and does not have a good chance of escaping. And then you define the conductance of this random walk overall as just the infimum of the conductance of a set over all sets S. And much like Cheeger's inequality in random walks on graphs, you have a similar thing here, where you get that, the total variation distance to the uniform distribution decays exponentially with the squared conductance of the random walk. So what this means is that the mixing time of the random walk is O of 1 over the conductance square times log of the warmness parameter, which is what we said we wanted earlier when we were talking about cold starts, right? So if we manage to show that this conductance is polynomial in n and the aspect ratio, then we're done. Then we get that the random walk mixes from a cold start. Now to actually show these conductance lower bounds for random walks, we end up usually proving these isoparametric inequalities, which essentially means that you have two subsets which are far apart in some metric, where we might have to design this metric specifically. And then you want to show that the remaining part of this body, so the measure excluding these two sets, is significant. So let me next get into a little bit of the history of the hit and run and coordinate hit and run random walks I mentioned a few slides back. So in the 90s, Lova showed that the hit and run walk mixes from a warm start. And a little bit later, Lovash and Vempala proved that it in fact mixes from a cold start. And their proof strategy was again using an isoparametric inequality like I mentioned in the previous slide. And they sort of refined this isoparametric inequality, which was originally shown by Lovash in his paper from the 90s. Now for coordinate hit and run, on the other hand, it seems efficient in numerical implementations. And quite recently, in the past 2-3 years, it has been shown that coordinate hit and run mixes from a warm start. But up until now, it was unknown whether it mixes fast from a cold start as well. One would believe that this is true because hit and run mixes from a cold start and coordinate hit and run seems similar to hit and run. But for whatever reason, the two walks seem incredibly different, at least in terms of the analysis. Now let me get into our results. And before doing that, let me get into a little bit of setup for the results. So first, we have this thing called a Whitney decomposition of the body specific to a parameter P greater than 1. This was originally done by Hausler-Whitney back in the 1900s. And essentially what this does is that given your convex body K, it decomposes it into a bunch of disjoint cubes. Disjoint in the sense that their interiors don't overlap. And each of these cubes are special in that their diameters are within a constant factor of the distance of any point in the cube to the boundary, right? So the diameters of these cubes scale with the distance to the boundary. And furthermore, there is this bounded geometry in the decomposition, which means that if you have any two abutting cubes, their diameters are within just a factor of 2 of each other, right? And in fact, it's just 1 or 2 because all the side lengths are some power of 2. So over this Whitney decomposition, we define a Markov chain. And the way this Markov chain is defined is that suppose I am at some cube Q. What I first do is that I uniformly randomly pick a point on the boundary of Q. And then I propose a move to the other cube Q prime, which is also incident on this point that I have chosen on the boundary. And then with some acceptance probability, I accept this proposed move. So this acceptance probability is just in order to ensure that the final stationary distribution of this Markov chain is the distribution we are interested in, which is the analog of the uniform distribution on the convex body. So our result shows that this Markov chain mixes fast from a cold start. So what we show is that the conductance of the Markov chain, of this MP Markov chain, is just some inverse polynomial in terms of the dimension and the aspect ratio. And consequently, we get that the mixing time of this Markov chain is some polynomial in the dimension n, the aspect ratio r over r, and log of the oneness parameter. And as a corollary, we get that the coordinate hit and run walk also mixes rapidly from a cold start, albeit with a slightly worse mixing time bound, going from n to the 4 for the multiscale walk to n to the 9 for the coordinate hit and run walk. And as I mentioned earlier, you can massage this result a bit and show that you also get mixing from a point as long as this point is slightly far from the boundary. So the proof sketch roughly follows that of Ladha and Vempala from 2021, and we show that if you can bound the conductance of the multiscale M infinity chain, then with a suitable modification of their proof, you can bound the conductance of coordinate hit and run as well. And then we bound the conductance of the M infinity chain. So I mentioned earlier that many of these conductance lower bounds essentially amount to isoparametric inequalities. So let me first define this metric GP, which is what we will be defining, which is what we will be proving an isoparametric inequality for. So what this GP metric looks like is that we take the L infinity metric, except that if we are at a point X, the L infinity metric is scaled by the distance of this point to the boundary of the convex body. So more rigorously, we define this length of differential path between 2 points, which is, as you can see, first we have this L infinity metric part in the numerator, and in the denominator we just scale it by the distance of that point to the boundary, and then we define the overall GP metric as just the infimum overall paths. Now our isoparametric inequality looks something like this, and what it says is that if you partition your convex body K into 3 sets, such that 2 of the sets, S1 and S2, are somewhat far apart in this metric, then in fact the remaining part of the partition, S3, also has significant volume, and the significance of course depends on the volume of, say, the smaller of S1 and S2, as well as the distance between S1 and S2. And actually our proof is stronger than this, and it shows that this isoparametric inequality is stronger when the volume of the smaller of the two sets, S1, is incredibly small, so it's exponentially small. So let me next get into a proof sketch of the results in our paper. So first I'll show how this isoparametric inequality implies a conductance bound for the MP, for the multiscale Markov chain. After that, I'll give a proof sketch of this isoparametric inequality itself, and then I'll give a proof sketch of how a conductance bound for the multiscale Markov chain implies a conductance bound for the coordinate hit and run random walk. So let me next get into how the isoparametric inequality implies a conductance lower bound for our multiscale random walk. So in the isoparametric inequality, we have these 3 sets, S1, S2, and S3. So if we are interested in bounding the conductance of a set S of cubes, then first we just set S1 to be the union of all these cubes. And then we define S3 to be a delta expansion of the set S1, which just means that you take all points within a GP distance of delta from S1, and then you remove S1. So for example, if we are interested in bounding the conductance of these pink cubes, you first set S1 to be just the union of all these cubes, and then S3 is just a delta expansion of these, and S2 is everything else. So the important thing to note here is that the distance by which we are expanding each of these cubes to get S3 is thicker near the middle of the body and thinner near the boundary of the body. And more precisely, it's in fact proportional to the diameter of the cube which you are expanding due to the nature of these Whitney cube decomposition. And as a consequence of this, it sort of captures the fact that you make bigger steps near the middle of the body and smaller steps near the boundary of the body. And with the bounded geometry property of the Whitney cubes, it captures this transitioning that the the multiscale walk does. So next, let me show how you actually prove this isoparametric inequality. So first, if you consider the case where a lot of S1 is far from the boundary, then if you actually look at our GP metric, because we are scaling it by the LP distance to the boundary, if it's far from the boundary, then we can in fact lower bound this LP distance by something. So we can show that it does not distort the L infinity metric by too much. So we can get away with just proving an isoparametric inequality for the L infinity metric instead of our GP metric. And such an isoparametric inequality is already known, so we are done. The next case is when there is a lot of S1 close to the boundary. So to analyze this, we used an argument which is inspired by Kannan-Lovar-Simonovitz from the 90s, which is a needle-based argument. And what this means is that you partition the convex body K into a bunch of needles, which are very thin radial objects emanating from this point in the middle of the body. And then you analyze each of these needles separately. So then, given these needles, we partition it into two types of needles. First, you have the good needles, which means that within the needle, most of the S1 is close to the boundary. And then you have these bad needles, where a lot of the S1 is far from the boundary within the needle. And then we show that on each of these needles, there is a significant amount of S3 in comparison to S1. And if we have that there are many good needles, then we are done, because then we just integrate over the needles and show that there is in fact a lot of S3 compared to S1 in the convex body as a whole. And yeah, as I've written, the analysis on each of these needles is essentially one-dimensional. Next, let me sketch how the conductance bound for the multiscale walk implies a conductance bound for the coordinate hit and run walk. So it turns out that to bound the conductance of coordinate hit and run, you want to prove a so-called L0 isoparametric inequality, which means that you want to show an isoparametric inequality in the setting where your two sets S1 and S2 do not share any axis aligned line. So these two lines that I have drawn, horizontal and vertical, they are axis aligned and do not intersect both S1 and S2. And more generally, my requirement is that there is no such axis aligned line which intersects both S1 and S2. So first, let me consider the set S1. What I do is I superimpose this picture of the Whitney cubes that I have, and I split the set of Whitney cubes in two parts. So first I have the cubes which contain a lot of S1, so which is all these green cubes that you can see which contain a significant amount of S1 within the body. And then I have all these bad pink cubes which do not contain much S1. After that, I show that if I have a bad cube that is adjacent to a good cube, then this bad cube must necessarily contain quite a lot of S3. And then after this, I show that there are in fact many such bad cubes adjacent to good cubes using the conductance of the multiscale walk itself. So let me now give a brief summary of what we looked at in the STOC. So first we introduced this new family of Markov chains for sampling from convex sets, which is a walk over this Whitney cube decomposition of the body. And this sort of exploits this nice bounded geometry property that the Whitney decomposition has. And this GP metric that I have captures the fact that near the middle of the body I make big steps, and near the boundary of the body I make smaller steps. And as a corollary, I get that coordinate hit and run rapidly mixes from a cold start using these multiscale chains as a tool. And yeah, that's all I have. Thank you for listening.